Warning: Earth's core has reversed, and time is glitching. Telemetry spikes. A satellite over the South Atlantic goes blind for 10 minutes, then reboots like nothing happened. In a Midwestern lab, a seismologist watches two identical earthquake waveforms, separated by decades, refuse to match. And under your feet, the planet's iron heart has slowed, then started edging backward. That's not doom, it's a change in rhythm. Here's the setup. Evidence now suggests Earth's inner core entered a slowdown and reversal phase tied to multi-decade oscillations. Meanwhile, the magnetic shield has a growing dent over the South Atlantic, and some people swear time itself feels off. If the planet's clock slips, even by milliseconds, do we? To answer, we rewind to the data. Three revelations hold this story together. First, the core's turn isn't a movie flip. It's a subtle, decadal swing you catch only if you stack the right echoes. Seismologists compare doublets, earthquakes from the same patch, recorded along nearly identical paths across years. Their travel times through the inner core stopped shifting the way they used to around 2009 to 2010, consistent with a slowdown and direction change within a roughly 60 to 70-year cycle, reported by multiple teams, including Song and Yang. Not everybody agrees on the amplitude, but the pattern keeps showing up. And that unresolved gap is exactly what keeps scientists and us leaning in. Second, the dent in the sky is real. The South Atlantic Anomaly, where the field at satellite altitude sags and trapped protons dive lower, has broadened and even split into lobes in recent maps from missions like Swarm. Operators treat it like weather now, scheduling safe modes to survive the crossing. It's not a flip countdown, it's a live hazard band that drifts, proof that regional magnetism can misbehave while the global field holds. Third, the human piece. Time. Atomic clocks ignore the core, but the planet doesn't. Length of day nudges by milliseconds as mass redistributes and deep flows evolve. You won't feel that directly, but systems that stack precise timing, navigation, grids, satellites, can. And our perception? It's messy, driven by stress, daylight, attention. Claims that Earth's heartbeat makes days feel like 16 hours don't hold up. But noisy infrastructure does change how smooth reality feels. We'll follow those threads. Seismic proof of a turning core, the magnetic dent, and the deep structure beneath Africa, and the lived friction when space weather punches a moving target. First stop, catching the core in the act. Seismic smoking gun, catching the core's turn. To see a sphere you can't touch, you listen for echoes it can't hide. Seismologists learned long ago that certain earthquake waves shoot straight through the inner core, bounce and return along near-repeat paths. If the core rotates a little faster or slower than the mantle, the iron lattice those waves traverse isn't aligned the same way each decade. Travel times shift by fractions of a second. That's the fingerprint. The path names sound like code. PKIKP for a wave that goes down through the mantle. P cuts the outer core, K passes the inner core, I, then back again. Take two similar quakes from the same patch on the globe, recorded at the same station, 20 or 30 years apart. Subtract their waveforms. For years, that differential drift suggested the inner core slipped ahead of the mantle. Then around 2009 to 201, the drift flattened and began to reverse in some paths. The simplest read: the inner core nearly ceased overtaking the mantle and started edging the other way, part of a multi-decadal oscillation. Pause on what reversal means here. The inner core isn't a free-spinning ball changing absolute direction. It's rotating relative to the mantle, slightly faster, slower, or even lagging. The change of sign is about differential motion, not a gear clank. And it's not instant. Think of it as a long exhale, then a slow inhale, a phase that builds over years. The hook. If the heart of the planet changes tempo, what else syncs or desyncs with it? Why would the core behave like this? Two couplings fight for control. Electromagnetic coupling. The geodynamo in the liquid outer core drags on the inner core through magnetic fields, trying to speed or slow it. Gravitational coupling. Slight asphericities tie the inner core to the mantle, tugging it back toward alignment. If the magnetic torque strengthens, the inner core can pull ahead. If it weakens or flips sign as flows reorganize, gravity's leash wins for a while. Add viscous coupling at the boundary, and you get a system that likes to oscillate. Models predict cycles on the order of decades, and independent observations line up. Variations in length of day, millisecond-scale jitters, show a 60 to 70-year rhythm. Secular variation in the magnetic field carries similar beats. The new seismic read fits that family. A turning point in the early 1970s, another, near 2010, consistent with a roughly 70-year swing. Not everyone buys the exact phasing or amplitude, but the decadal seesaw keeps appearing in different data sets. The kind of pattern that begs for an explanation you'll want to hear through to the end. Here's where the word smoking gun earns its name. It's not one waveform, it's stacks of repeating quakes whose PKIKP phases changed relative to their cousins. It's waveform differentials that converge across studies using distinct catalogs and stations. It's a picture that improves as networks densify. In the 1980s, you might have had a handful of clean pairs. Today, with global arrays and better clocks, you can build time series with enough coverage to see the curve bend. And yet, the core won't sit still for clean narratives. Seismologists argue over anisotropy, the inner core's directional stiffness, and how its evolving texture biases travel times. Some studies suggest the inner core's uppermost shell is changing structure, complicating the inference. Others propose regional heterogeneity. Waves sampling one sector may tell a slightly different story than those sampling another. That's science working. The broad oscillation hypothesis stands, the details sharpen. What matters for us is that the direction change isn't academic. When the inner core's relative spin shifts, it adjusts how angular momentum trades between deep layers and the mantle. The effect on day length sits in the thousandths of a second, but it's measurable, and it correlates with the seismic timing. Meanwhile, the outer core's flows, the real engine of the magnetic field, are coupled to this dance. If the magnetic torque on the inner core is changing, the geodynamo's pattern is too. That's a subtle nudge on the field we live inside. Micro stories make it human. In Beijing, a researcher overlays PKIKP pairs from Alaska quakes, recorded in Europe, and watches the residuals flatten across the 200s. Years of work distilled into a quiet line. In Los Angeles, a team reprocesses digitized analog tapes from the 197s, aligning time bases to salvage microseconds from paper. In Paris, a group runs inverse models that let the inner core's anisotropy evolve, and finds they can fit both the waveform drifts and the LOD wiggle with a single oscillation. None of them claim the last word. They publish, criticize, refine. A natural question: is this the same kind of reversal as a magnetic pole flip? No. Magnetic reversals are wholesale reorganizations of the geodynamo that play out over centuries to millennia. The inner core's oscillation is a decadal wobble in relative rotation, small, recurrent, and already baked into Earth's long-term behavior. But the two aren't divorced. A dynamo that breathes on decadal scales seeds the slow evolution that, once in a long while, tips the whole field into an excursion or reversal. Today, we're watching the breath. There's one more turn in this beat. The same community that listens for PKIKP differentials also listens for torsional oscillations. Shear waves of faster and slower rotation sloshing through the outer core. Those waves can modulate the magnetic torque on the inner core, reinforcing or opposing the gravitational tug. Catch a torsional pulse in the secular variation and a turning point in the seismic residuals, and you've got a synced drumline. That's the promise of the modern instrument stack. Satellites mapping field change, observatories watching drift, and seismology timing the heart. So yes, the inner core slowed and began to backtrack relative to the mantle, likely part of a multi-decade oscillation. The evidence isn't a single plot. It's a chorus of echoes that change key around 2010. Next, we follow that change upward, because when the engine shifts, the shield it powers shows it first. The magnetic shield with texture. To understand what changes first, step into the field we live inside. It isn't a smooth dome. It's a layered, moving system shaped by a metal ocean 2,900 kilometers down and a star 150 million kilometers away. At its core is the geodynamo, liquid iron churning, dragging magnetic field lines into loops that, time average, look like a tilted bar magnet. That big dipole is only the bass track. Riding on top are smaller harmonics, lobes, patches, kinks, that drift, merge, and fade. Texture is the right word. You don't cross one shield, you cross a pattern. Up in space, those patterns set the plumbing. Field lines bundle into curtains that guide charged particles into the Van Allen belts. two donuts where protons and electrons bounce between mirror points. When the dipole is strong and centered, the belts sit high and tidy. When the field sags regionally, the inner belt droops closer to low Earth orbit. That's the South Atlantic Anomaly in practical terms. A thin spot where trapped protons come down to meet satellites that would rather not meet them. Mission logs read like weather diaries. Hub's operations. Plan has dark bands. No observations when its orbit skims the anomaly. On the International Space Station, radiation monitors tick higher in the same longitude. CubeSats with consumer-grade memory cross the hot zone and wake up rebooted watchdog timers, having hauled them back from nonsense. Engineers plan around it. Instrument safe modes, lower high-voltage biases, error-correcting memory scrubbed faster during the pass. You see the dent on data maps as rectangles of missing images over the South Atlantic. Gaps by design to save detectors. Meanwhile, the anomaly isn't standing still. Magnetometer constellations, Orsted, Champ, then ESA's Swarm, have watched its footprint broaden and more recently split into twin lobes. The centroid drifts west and a bit south year by year. It's a living hazard band. On some orbits, the worst flux sits farther east than last season. Operators update masks the way pilots update turbulence forecasts. The difference here is invisible. No cloud tops to glance at, just tables and models that say, power down from 1312 to 1326 Universal Time Coordinated. Curiosity gap. If a dent can split and move, what's yanking it around from below? Why that patch there? The answer starts far below Africa. At the core mantle boundary, maps show a persistent reversed flux patch, field lines pointing opposite the global dipole beneath southern Africa. Above it, seismology images one of Earth's two giant deep mantle structures, the African LLSVP, a thermochemical plateau that modulates how heat leaks out of the core. Uneven heat loss steers core flows. Core flows shape magnetic patches. Stubborn reverse patch drags the dipole off-center and weakens the surface field over the South Atlantic. The belts respond downstream by slumping. Quiet days tell one story. Storm days rewrite it. When the sun launches a coronal mass ejection and the interplanetary magnetic field turns south, reconnection cracks open the magnetopause. Energy couples in, belts swell, and particle flux climbs at altitudes that are usually safe. Over a weak field corridor like the anomaly, the same solar punch drives stronger currents and deeper access. Spacecraft ride it out with widened masks and conservative modes. A telescope loses an observing block. A GPS satellite sees a momentary phase jump that downstream system smooth with redundancy. Reliability survives on margin. The dent trims margin. Not everything with texture lives in orbit. The field's regional complexity shows up on the ground too. Ground observatories in South America and Southern Africa record secular variation that bends faster than elsewhere. Pipeline operators in Brazil watch geomagnetically induced currents during big storms and adjust cathodic protection. The grid in Southern Africa has procedures for storm nights, reduce long-haul transfers, keep transformer neutrals cool, because long wires make good antennas for changing magnetic fields. Again, it isn't apocalypse. It's operational life under a noisier shield. One microstory stands in for many. A star tracker on an Earth imager begins returning off-the-wall quaternions right over the eastern lobe. The flight software refuses to believe them, hands off the gyros, and keeps pointing within spec. An engineer adjusts the tracker's proton flag thresholds and extends the mass by 90 seconds. The next pass, the attitude plot is boring. That's the goal. The headline temptation is to read the anomaly as prophecy. It isn't. South Atlantic weakness doesn't set a date for a flip. It's a recurring trouble zone in the paleomagnetic record, a place the field likes to misbehave while the global dipole persists. That makes it the right place to watch. When the engine shifts, this is where the first seams show, and the next layer down, beneath Southern Africa, is where we go next to see why the seam sits there at all. Africa's deep engine, flux patch over a mantle giant. To find the dense route, drop to the boundary where liquid metal meets solid rock and look up at Africa from the core side. The map down there doesn't show countries. It shows magnetic polarity. Most of it agrees with the global dipole. One stubborn province does not. Beneath Southern Africa sits a reversed flux patch, a compact blot where field lines point the opposite way. It's been there off and on for centuries in the records. It's not decoration, it's leverage. Now tilt your gaze into the mantle above. Seismic waves crossing the deepest layers slow over a continent-sized plateau called a large, low shear velocity province, the African LLSVP. It isn't molten, but it's hotter and likely compositionally different than surrounding mantle. Thicker blankets piled across the core. Where a blanket is thicker, less heat escapes. Where the edge thins, heat pours out faster. That patchwork of heat loss sculpts the core's flow. Fast columns next to slow ones, eddies that kink field lines, patches that flip polarity locally and refuse to budge. The African LLSVP sets the stage. The reversed flux patch delivers the scene. Numerical dynamos make this link visible. Feed a model with an African-style heat flux pattern at the core mantle boundary, and the solution reliably grows a reverse patch under southern Africa. Let the patch ride, and the surface field above weakens and skews. The South Atlantic Anomaly is the downstream expression of that skew. In runs that include long-lived thermochemical piles, the patch survives, splits, and reforms. Behavior that rhymes with swarms evolving maps. Remove the deep mantle structure, and the patch loses its anchor. This is causation you can't drill, but you can test with physics. Archaeology backs the timescale. In Iron Age kilns across southern Africa, clay cooled in fields that were anomalously weak. Those archaeomagnetic intensities sagged for centuries, then recovered. Offshore sediments record matching dips. Independent materials, same century-scale softness over the same region. The message is consistent. The African sector is a repeat offender, not a one-off blip. Here's the tease will pay off. This is the same neighborhood where core models grow a reversed flux patch when you feed in Africa's deep mantle heat map. Meanwhile, geophysicists argue useful details. How much of the LLSVP's identity is thermal versus chemical? Thermal blankets change faster. Chemical piles are sturdier. The best evidence favors a thermochemical mix, long-lived but lumpy on top. That hybrid explains the paradox. A tendency that persists for tens of millions of years, and a surface field that breathes on decadal to centennial scales. A stable base, a restless roof. Human moments make the deep map tangible. In a Cape Town archive, a researcher catalogs kiln fragments with sun compass marks, because a normal compass will lie near iron-rich rocks. Down the hall, a modeler nudges the LLSVP edge steeper in code and watches a reverse patch swell beneath Africa, then slide west a hair. On a shared corkboard, a pottery intensity series and a simulation snapshot sit side by side. In pencil, someone writes, "Close." There's a temptation to make the African patch a villain foretelling reversal. It's not a prophecy. In many dynamo simulations that reverse, large reverse patches do expand before the dipole reorganizes. In many that don't, the patches pulse and shrink without tipping the system. The sober phrasing is this: a strong African reverse patch increases the probability of messy maps, more non-dipole structure, more regional weakness, without dictating the ending. What it guarantees is a place to watch, and a reason to keep asking what the next decade does to the dent you can't see. Watch from space and you see the consequence instantly. Because the dipole is dragged off center, the inner radiation belt slumps closer over the South Atlantic. Because the belt is closer, satellites feel more protons and schedule more naps. Watch from the ground and you see earlier storm coupling in magnetometer traces, transformer neutrals that need attention, pipeline potentials that drift. Same, because different instruments. One more mechanism links core and patch. Torsional oscillations, broad shear waves of slightly faster and slower rotation in the outer core. Slosh along columns aligned with Earth's spin. When those waves reach the African sector, they change magnetic shear across the reverse patch. That modulates the magnetic torque on the inner core above and the surface field above that. Catch a jerk in the secular variation, a seismic turning point, and a small drift in day length within a few years. And you're seeing the composite, inner, outer, and mantle singing one bar together. The meaning isn't doom, it's geography. Earth's magnetic field isn't centered fairness, it's a field with neighborhoods. Southern Africa sits atop a deep structure that steers core weather, and core weather writes the dent in the sky. That's why the anomaly shifts like a living thing, and why the first seams show there. From here, the causal chain runs upward and outward, to space weather hitting a moving target, to operators treating magnetism like weather instead of a map. And when solar energy tests our shield, this is where the proof
clocks
lands
and
first.
glitches. We actually measure. Start with the cleanest clock we've ever built. Atomic time doesn't care about molten iron. Cesium atoms flip at the same frequency on a quiet Tuesday as during a solar storm. That's why we define the second there. Planetary time is messier. Earth's rotation wanders by milliseconds as winds push, oceans slosh, ice shifts, and deep interior torques trade angular momentum. That drift shows up in the length of day record, a jagged line with seasonal wiggles, a 6-year beat, and those longer 60, 70-year sways tied to core dynamics. When the oscillation we traced in the inner core turns, the rotation budget adjusts. The change is tiny, but it's real, and timekeepers fold it in. Here's how that accommodation works. International time stewards run 2 tracks. UTC, the time in your phone, follows atomic seconds, but occasionally adds or removes a leap second to keep civil clocks close to Earth's rotation, UT1. The leap decision rests on precise geodetic measurements. Lasers bounced off satellites, GPS phase, radio interferometry linking antennas continents apart. The adjustments feel bureaucratic. They're really a handshake between atoms and a spinning planet. If the inner core's torque nudges rotation, do we look up and feel days shrink? No. A millisecond change is below perception. But systems that synchronize precisely do feel it. GPS satellites carry atomic clocks and broadcast time. Receivers on the ground solve for position by comparing arrival times from multiple birds. Space weather and ionospheric delays add noise. Weak field corridors make that noise spike. During lively solar days, ionospheric irregularities above South America distort signals. Aviation procedures switch to alternate navigation. Surveyors pause high-precision work, and timing networks lean on holdover oscillators until the sky calms. Meanwhile, power grids run on choreography. AC grids must keep frequency tight and phase aligned across long wires. Geomagnetically induced currents from storm-time magnetic swings add a slow bias to transformers. That bias can push equipment towards saturation, heating it, and distorting waveforms. Operators watch neutral currents and temperature and adjust dispatch to keep phase coherent. Timing enters twice. In protection relays that act within fractions of a cycle, and in wide area measurements that compare voltage phase angles across regions using GPS-disciplined clocks. If satellite timing stutters for a moment during a storm, phaser systems trust redundant paths or local oscillators. The dance continues because someone rehearsed it. In space, timekeeping gets more literal. Satellite payloads gate high-voltage detectors and star trackers on schedules computed to the second for South Atlantic crossings. Extend a mask by 90 seconds and you've just traded a slice of observing time for months of instrument life. The clock is a shield as much as a ruler. Now to the human rumor. Time glitches, days that feel like 16 hours, Earth's heartbeat spiking. The physics is blunt. The Schumann resonances are standing electromagnetic modes in the Earth ionosphere cavity, driven by lightning. Their fundamental sits near 7.83 Hz and varies modestly with season, solar activity, and ionospheric state. They're used to remotely sense the ionosphere, not to measure consciousness. Claims that they jump to tens or hundreds of hertz and compressed our days misread spectrograms and confuse intensity with frequency. Your perception of time does stretch and compress, but because of attention, stress, sleep debt, and circadian misalignment, not because the cavity vibrated differently that afternoon. There is, however, a bridge between field noise and lived friction. During strong storms, HF radio degrades, satellite navigation gets noisy, polar flights reroute, and communication handoffs slow. Operations stack small delays. A detour adds an hour. A satellite drops a pass. A telescope splits an exposure. A grid operator holds a lower transfer. A dispatcher's day fills with exceptions instead of routines. To the people inside those shifts, reality feels jittery. That's not metaphysics. It's the texture of infrastructure and weather. Micro stories make that vivid. A medevac crew launching from Patagonia loses HF for 10 minutes and switches to SATCOM. It works, but the call tree is longer, the cadence off. In Sao Paulo, a timing engineer watches a GPS receiver flag, a transient, and sees the backup oven-controlled crystal slide in, holding phase until the sky recovers. In a control room, a phaser display keeps painting clean angles because a second timing feed, fiber-delivered time from an atomic source, was funded last year, nobody outside notices. The point is precisely that they don't. Even at the planetary scale, the clock has buffers. When Earth's rotation drifts, leap seconds keep civil time within a second of UT1. Some institutions hate leap seconds because they complicate. There's an active move to retire them. If that happens, UTC will decouple from Earth's spin and drift slowly. Centuries from now, noon on your clock would slip from the sun overhead. That debate belongs to standards bodies, not solar storms. But it tells you something about human time. We bend the definition when it helps. So yes, the inner core's oscillation shows up in millisecond nudges to day length. Yes, the magnetic dent and solar weather add noise to the timing fabric machines rely on. No, the planet didn't cut our day in half. What we feel are the seams of coordination. The cure is boring. Redundancy, better models, and the humility to treat magnetic weather like weather. Forecast it, budget for it, and keep the clock steady while the heart beats irregularly underneath. When the sun punches a moving target. Space weather has beats of its own. The sun breathes in an 11-year cycle, and on its exhale, it hurls flares and coronal mass ejections, vast bubbles of magnetized plasma across the solar system. Most miss, some don't. When one arrives and the interplanetary magnetic field turns south, opposite Earth's near the day side, magnetic reconnection snaps open the magnetopause like a door on a windy day. Energy pours in, races down field lines, and lights auroras. Beauty is the surface. Underneath, currents roar. Those currents set the rules for what fails first. In the ionosphere, conductivity jumps and radio waves refract differently. HF bands go patchy or black, and systems that depend on them, polar aviation, oceanic traffic control, some military links, shift frequencies or fall back to satellites. In the magnetosphere, the radiation belts inflate. Electrons surge inward. Protons flood usual safe lanes, and low Earth orbit turns grainier for any instrument that hates charged particles. That's normal hazard under a steady shield. Now add texture, a weak field corridor drifting over the South Atlantic, and the same solar punch couples harder and deeper. Grids feel it through the ground. Changing magnetic fields induce electric fields. Long conductors, power lines, pipelines, undersea cables pick up quasi-DC currents called geomagnetically induced currents. Transformers don't like DC. It drives their cores toward saturation, distorting the AC waveform, generating heat, and confusing protective relays. In March 1989, a storm saturated a key transformer in Quebec. A cascade tripped the province off in under 2 minutes. The fix since then hasn't been hope. It's planning real-time JIC monitors on transformer neutrals, series capacitors to block DC on long lines, procedures that reduce long-haul transfers when an alert comes in, and spares programs because some hardware, once cooked, takes months to replace. Satellites live inside the punch. During a storm, teams raise charging thresholds, widen South Atlantic masks, drop high-voltage biases, and accept lost data to save detectors. Deep dielectric charging, the slow burial of energetic electrons in insulation, becomes the silent threat. Hours later, a discharge can flip a bit or freeze a board. Error-correcting memory and configuration scrubbing catch a lot. Not all. Mission logs after Halloween 2003 read like a storm diary. Safe modes, resets, phase returns to service. The modern difference is foresight. Coronagraphs spot halo CMEs. Models predict arrival times, with uncertainty that depends on the CME's magnetic orientation. And ops timelines shift before the shock hits. Navigation feels the storm in the sky itself. Ionospheric irregularities mess with GPS signals, adding delay and scintillation. A survey crew in Argentina pauses centimeter-level work because the vertical ionospheric delay estimate went wild. An airline dispatcher slides a polar route south because HF is unreliable, and dose advisories nudge planning. A receiver tracking multiple constellations, GPS, Galileo, BDU, rides out the patch because diversity buys margin, and because aviation procedures train crisp fallbacks to inertial and radio navigation when integrity flags pop. A timing network feeding phaser measurement units trusts its local oven-controlled crystal for an hour because someone funded fiber-delivered time as a backup to satellites. None of that is dramatic. It's the stitched redundancy that makes storms survivable. Weak field corridors shrink headroom. Over the South Atlantic, The same event drives larger ionospheric currents and lifts particle fluxes at lower altitudes. A telescope that would have risked an exposure in last cycle's maps splits it now. A CubeSat that would have squeaked through resets twice instead dies young from flash memory wear. Operators don't need philosophy to explain it. Their tables tell them the rates. They adjust. There's a human timeline to a big day. A forecaster watches a halo sweep across a coronagraph, dials a model, and posts an alert. Arrival in 36 hours, IMF orientation uncertain. Utility control rooms call extra staff, reduce transfers on long east-west corridors, and set transformer thermal alarms tighter. Satellite ops widen masks and press send on configuration changes. Aviation weather centers issue radiation and HF advisories. Dispatchers pencil extra fuel and alternate routes. The storm arrives. Magnetometers spike. Auroras spill to unusual latitudes. A transformer neutral current rises and then flattens at a safe plateau. A satellite rides through with dull telemetry where a spike would have been. A polar flight adds an hour and lands uneventfully. The news shows red skies, the logs show boring curves. That's success. Pipelines sit in the same loop. Storm time telluric fields bias cathodic protection systems. Operators watch pipe-to-soil potentials and tweak current to avoid underprotection that speeds corrosion or overprotection that wastes power. Undersea cables have their own sensitivities, repeaters fed by DC, and designers account for storm biases in station equipment. The theme repeats. Long conductors make good antennas. The cure is measurement and response. None of this means storms became stronger because the core breathed differently. It means access changed. A lumpy, modestly weaker field opens more doors for the same solar energy. The right response isn't panic. It's treating magnetic weather like weather. Forecast the front. Build levees where the water runs. Drill crews on the Playbook. The sun will throw another punch. Our job is to make sure it lands as a long night at work, not a morning without power. The weird old skies, excursions and reversals in the record. To know how strange the sky can get, you have to read time written in rocks, ice, and clay. Start with Lashchamps, about 41,000 years ago. The global dipole didn't vanish, but it slumped hard. Paleomagnetic records from lava flows and lake sediments show intensity falling to a small fraction of today's value, while directions wandered far from the usual north-south. In Greenland and Antarctic ice, cosmogenic isotopes, beryllium, tin, and radiocarbon, spiked at the same time, signatures of extracosmic rays punching deeper into the atmosphere under a softer shield. If you were alive then, you probably didn't know a name for it. You might have seen auroras at latitudes where stars usually kept their color, a quiet strangeness folded into ordinary nights. Here's what didn't happen. There's no evidence of extinction tied to the Lashchamps excursion. Plants and animals adapted. People kept making tools, painting, crossing water. Ozone chemistry likely shifted a bit under increased particle showers, nudging ultraviolet up beneath clear skies. But the biosphere held. Excursions like Lashchamp are messy middles. The field weakens, grows multipolar for centuries, then recovers its original polarity. That's the important distinction. A full reversal takes hundreds to a few thousand years and ends with the dipole rebuilt pointing the other way. An excursion wanders and comes back. Mono Lake, a few thousand years later, tells the same kind of story in miniature. Lava and sediments around the Great Basin preserved directions that swung dramatically, then settled without flipping. An excursion, not a reversal. Across many sites, you see a pattern. Intensity plunges, directions meander, isotope production climbs, and then the field rallies. None of these episodes required a countdown. They arrived as oscillations in the deep engine expressed in the sky. Zoom out to the long record and reversals become chapters. The Brunnenskron we live in is normal, polarity for the last 780,000 years. Before it lies the Matayama, mostly reversed. Farther back, polarity flips stack through Earth history irregularly. The geologic reversal record shows variable spacing, with supercrons and tighter clusters. The spacing isn't clockwork. Sometimes millions of years separate flips. Sometimes the cadence tightens. Paleomagnetists built this timeline by sampling lava sequences that cooled through their Curie points, locking in the field's direction, and by reading magnetic grains aligned in sediments layer by layer. The method isn't romantic, it's careful. Orientation marks, stepwise heating, demagnetization to peel off overprints, independent dating to fix time. The result is a map of the field's moods. Now pull the camera to the South Atlantic sector. Archaeomagnetism, the field recorded in fired clays and hearths, across southern Africa, shows century-scale dips in intensity 2 to 3 millennia ago. Offshore sediments echo the softness. Those localized lows fit the idea we traced earlier. This region is a repeat trouble spot. In reversal simulations that include African-style core mantle heat flux, reverse flux patches blossom here, sometimes spreading to tip the dipole, sometimes pulsing and shrinking without crossing the line. The record says both modes are natural. What did people notice? Where there's writing, there are hints. Historical chronicles farther north describe blood-red auroras appearing unusually far from the poles during strong storms. Not because the field flipped, but because access opened. In weak field eras, the same solar punch pushes farther. The practical effects land on technologies in their era. In the 19th century, telegraphs sparked and paper smoldered during the Carrington event, 1859. In hours, we prepare grids, satellites, and aircraft. Past excursions aren't prophecies. They're field guides to what living under a noisier shield feels like. The isotope spikes matter for another reason. They give global timestamps that lock paleomagnetic stories together. When beryllium-10 and radiocarbon climb in ice and tree rings, at the same time lava records intensity lows and archaeomagnetism dips in southern Africa, you've got a triangulation, weak field, higher cosmic ray access, and regional misbehavior, all synchronized. That's how confidence builds without a drill core to the outer core. There's a tempting overreach in all this, to see Lechamp as a dress rehearsal for doom. The data argues otherwise. The atmosphere remains the primary shield at the surface. Even at last level lows, sea level dose barely budges compared with medical imaging or natural background differences. The risks spike for systems stretched across space and wire. Satellites, polar aviation, long-haul grids, pipelines. Those are modern problems with modern answers. Hardening, rerouting, monitoring, redundancy. Micro-stories tie eras together. In a cave in South Africa, a hearth's clay remembers centuries of low field while people cooked and talked. Near modern Mono Lake, a basalt flow froze a wild magnetic direction while a glacier retreated upslope. In a lab, a student measures a pottery shard's magnetization step by step, the needle steady until a temperature unlocks an ancient moment. The plot joins a stack on a wall. Next to it, a core field model shows a reverse patch under Africa growing and shrinking. Someone draws a thin line between them. Not cause and effect, but resonance. So yes, skies have been stranger. The field weakens, splits into lobes, lets the sun's energy thread deeper, then finds its way back. The lesson isn't terror, it's tempo. Excursions can last long enough to matter for generations while never crossing into a flip. Cultures adapt. In our era, adaptation looks like playbooks and forecasts. Which brings us back to now, separating myths from the data and deciding what to fortify when the map isn't fixed. Myths versus reality. What's likely, what's hype. Let's strip the noise from the signal. First myth, the core reversed. Apocalypse now. Reality. The inner core's reversal is a decadal change in relative rotation, not a flip of the planet's spin or a geodynamo shutdown. It nudges length of day by milliseconds and likely modulates magnetic torque. That's interesting physics, not a trigger for mass failure. The field we live inside is driven by the liquid outer core. Its long-term behavior doesn't hinge on the inner core swinging a few tenths of a degree per year relative to the mantle. Second myth, the South Atlantic Anomaly means a flip is imminent. The anomaly is a regional weak zone that has waxed, drifted, and split in recent decades. It matters for satellites and high-altitude operations now. But paleomagnetic and archaeomagnetic records show southern Africa has been a repeat trouble spot across millennia without the planet flipping every time. The SAA is a hazard band, not a countdown clock. Engineers are already flying it like weather. Masks, hardening, smarter autonomy. Third myth, Schumann Resonance spikes prove time is speeding up. The Schumann modes vary modestly with lightning, season, and ionospheric state, and they're useful for remote sensing. They don't jump to 120 hertz, and they don't compress civil time into 16-hour days. Perception is psychological. Timing networks are atomic. The real link between field noise and live friction is operational. Disturbed ionospheres, HF blackouts, nav noise, reroutes, and brief timing holdovers. That's logistics, not metaphysics. Fourth myth, magnetic north racing equals collapse. Pole wandering accelerates when non-dipole structure grows, but fast wandering has happened before without a reversal. It's a symptom of complexity, not destiny. Core flow inversions from satellite data accommodate it without demanding catastrophe. So what's likely? Three things. One, continued modest dipole decline on century scales with regional texture rising. That keeps the SAA moving target and raises upset rates in certain orbits. Two, deeper coupling pulses, torsional oscillations, and the inner core's multi-decadal swing continue to show up as coordinated beats in secular variation and length of day. We'll see more geomagnetic jerks and timing adjustments, not doomsday. 3. Storm risk concentrates where the shield is soft. Same solar punch, tighter margins over weak field corridors. That's a planning problem with established playbooks. What holds as true? Satellites will earn their lifetimes by design, not luck. Rad-tolerant memory, configuration scrubbing, shielding around clocks and high-voltage front ends, and SAA-aware scheduling are the difference between a mission that retires gracefully and one that dies in a reset spiral. Aviation will treat space weather like turbulence, with routine dose advisories, GNSS fallbacks, and HF alternatives. Grids will keep installing GIC monitors, neutral blocking, series capacitors, bigger thermal headroom, and running drills keyed to storm alerts. Multiplying timing sources, multi-constellation, GNSS, plus fiber-delivered time and robust local oscillators, keeps phaser systems honest when the sky crackles. Where uncertainty is real, predicting core flow beyond a few decades. We can outline scenarios because swarm-class maps, observatories, and seismology constrain the present. But small changes inside the outer core amplify. That's why scientists publish ensembles and error bars. It's also why continuity in measurements matters. Without the next magnetometer constellation and more ocean bottom observatories, the movie stutters and guesswork creeps in. Separate hype from stakes with a quick lens. Ask, is this claim consistent with multiple independent data streams? Does it require physics we already know? Does it scale with operational experience? Core reversal collapses, society fails all three. More instrument safe modes over the SAA next cycle passes. Time is shrinking because Earth's heartbeat jumped fails. Polar flights will reroute more often at solar max passes. The sober meaning is less dramatic and more useful. Earth's magnetic field is a living map. It's getting lumpier in places we can name, on timescales we can work with. The sun will keep testing that map. Our job isn't to panic at every headline. It's to keep watching the core breathe, keep the clocks honest,
Four futures,
harden the edges
from
where the
mildly
seams show
messy
first.
to full excursion. Think in playbooks, not prophecies. Over the next century, 4 futures bracket the odds, each one a different mix of core mood, field texture, and human response. Scenario A, baseline messy. The global dipole keeps sliding modestly. The South Atlantic Anomaly broadens, splits, and drifts like a slow tide. Satellites treated as moving weather. SAW-aware autonomy becomes standard. Instruments powered down automatically on geofence timers that update in orbit. Memory scrub rates rise on approach. Star trackers fuse gyro data more aggressively through the lobe. Constellations route tasks to birds in cleaner lanes. Radiation-hardened parts move from nice-to-have to default on long-lived missions. Upset rates climb but flatten under better design. Aviation turns space weather into routine. Dispatch dashboards layer radiation and HF health over winds and turbulence. Polar routes flex, dose budgets track crews in real time, and GNSS procedures bake in fallbacks without drama. Grids finish installing GIC monitors on critical transformers, add series capacitors on vulnerable east-west lines, and drill against alerts. Blackout headlines don't materialize. Line items and budgets do. The world notices mostly in the way quiet competence feels. More advisories, fewer surprises. Scenario B plateau. The dipole steadies as the core flow reconfigures. The SAA's twin lobes merge and soften. Upset rates ease. Operators reclaim minutes from masks and extend instrument duty cycles. The playbook's built-in baseline messy don't go to waste. They become maintenance.
This is what winning looks like in geophysics. Money spent, crises averted, and the explanation a little boring. Scientists chalk it up to a shift in core torque and torsional wave timing. Engineers keep the hardening because cycles turn. Scenario C, excursion. The dipole weakens a lot, half, then a third of today's strength over centuries without flipping polarity. Non-dipole structure blooms. Sow-like dents appear at new longitudes and slide. Satellites live or die by margin. Deep shielding around clocks and high-voltage front ends stops being negotiable. Config scrubbing is continuous. Orbits and local times are chosen to minimize weak lane crossings. Instruments that can tolerate background ride-through. Those that can't split exposures more often and accept gaps. Constellations stratify. Hardened platforms in low Earth orbit handle sensitive payloads, while cheaper birds do work that forgives resets. Aviation normalizes detours at solar max. Radiation advisories nudge schedules the way winter storms do now. HF reliability degrades more often. Alternate comms step in. Regulators update occupational dose frameworks with better storm forecasting, so crews don't carry the uncertainty alone. Grids lean into defensive posture. Neutral blocking devices and capacitors proliferate. Transformer cores with larger headroom become standard on long corridors. Regional agreements move spares faster. Wide area timing diversifies. Multi-constellation GNSS plus fiber-delivered time with robust local oscillators, so phaser systems don't blink when the sky hisses. It's costly without being catastrophic. People learn the cadence of magnetic weather like they learn pandemics and heat waves. Plan, adapt, continue. Scenario D, reversal in progress. The least likely inside a century, but the noisiest to manage. The field grows multipolar for generations. Local poles migrate unpredictably. Regional weak zones wax and collide. Birds and fish that navigate magnetically lean harder on stars and smell. Satellites feel a shifting archipelago of dents. Operators stop pretending fixed masks can keep up. Autonomy reads real-time field maps and space weather feeds to gate instruments on the fly. Hardware looks like deep space design. Thicker shields, triple modular redundancy everywhere. Fault isolation, so a spark stays local. Ground systems see more frequent, stronger geomagnetically induced currents. Utilities operate with storm posture as a background condition. Series capacitors and neutral blocks are everywhere. Transformer thermal margins are oversized. Load transfers are conservative on long east-west paths. Undersea cables and pipelines run enhanced monitoring permanently. Aviation treats latitude like a tide chart. Dose and comms drive tracks day by day. Polar shortcuts become rarer. The public sees auroras at mid-latitudes a few extra nights a year and shrugs after the first dozen. The internet keeps arguing about meaning. The lesson is simpler. Noisy middles can last longer than a lifetime, and civilization runs fine when it budgets for noise. Sector by sector, the playbooks rhyme. Satellites. Rad-hard memory as default, configuration scrubbing, SAA, and storm-aware autonomy, shielding around clocks and high-voltage detectors, orbits that minimize time in weak corridors, and insurance models that price inclination in local time, honestly. Aviation. Integrated dose routing in the flight management system, GNSS integrity monitoring with trained fallbacks to inertial and radio navigation, HF alternatives on tap, and routine crew refreshers key to space weather bulletins. Grids. E-key monitors on every vulnerable transformer, neutral blocking, and series capacitors on key corridors, transformer fleets with higher thermal headroom, dynamic modeling that ingests magnetometers, and drills that assume long-duration southward IMF. Timing, multi-constellation receivers, fiber time to critical nodes, and long holdover local oscillators. Forecasting. Coronagraphs at multiple longitudes, L1 sentinels, ground magnetometer arrays, ocean bottom sites, and data assimilation that turns measurements into guidance fast. Probabilities? Baseline messy, most likely. Plateau? Plausible. Excursion? Possible in a human planning horizon. Reversal in progress? Low odds soon, but worth the shelf-ready playbook because cycles don't ask permission. The connective tissue across all four is humility. The map moves. We live with it by watching the core breathe, treating magnetic weather like weather, and building enough slack that a long night at work stays a long night at work. Watching the core breathe, the new instrument stack. To watch a metal ocean move under continents, you need instruments that never blink and math that can separate whispers from weather. Start with satellites. The first modern picture came from Orsted and Champ, but ESA's Swarm turned snapshots into a movie. 3 identical spacecraft flying at different altitudes and local times, carrying ultra-stable vector magnetometers and accelerometers. By sampling the field from multiple heights and orbital geometries, Swarm lets modelers peel away the ionosphere's daytime loops and the magnetosphere's storm surges, leaving the slow baseline attributed to the core. Year by year, that baseline shows features drifting west, a reverse patch beneath southern Africa pulsing, and the South Atlantic weak zone stretching and splitting. Continuity matters more than glamour. Field models fade without overlapping missions, so the quiet crisis in this story is budget. To keep the movie running, follow-on constellations need absolute magnetometers with better calibration, orbits that precess through local time to catch external fields from new angles, and at least one high-altitude sentinel sampling the magnetosphere that confounds the core signal. The payoff is simple. Fewer assumptions, tighter uncertainties, and earlier flags when something in the engine changes tempo. Satellites aren't alone. Ground observatories, old domes with coils buried deep, record the field's direction and strength minute by minute. Some have done it for a century. Their time series anchor the inversion, catching geomagnetic jerks, abrupt changes in the rate of change that ripple through the network and hint at reorganizations in the outer core. Spread those observatories across continents and add ocean bottom magnetometers where the map goes blank and the interpolation stops guessing over oceans that cover most of Earth's surface. Data assimilation ties the stack together. Borrowed from weather forecasting, it blends measurements and physics in near real time. A core field model predicts tomorrow's field. New satellite and observatory data arrive. The algorithm nudges the model toward reality within uncertainties while respecting Maxwell's equations and the dynamo's constraints. The result isn't a pretty picture, it's guidance. Maps of core surface flows, confidence intervals on reverse patches, and forecasts of how the field will drift over the next few years. Operators can act on that. If the anomaly's eastern lobe accelerates, satellite teams widen masks before the particle counters prove it the hard way. Meanwhile, seismology adds a perpendicular view. Global arrays record earthquakes that sample the inner and outer core along different chords. Inversions of full waveforms refine the shape and stiffness of the inner core shell and the flow patterns implied by anisotropy changes. Torsional oscillations, shear waves of slightly faster and slower rotation, leave fingerprints in both seismology and magnetic secular variation. Catch them in phase with a length-of-day wiggle, and you've got synchronization across instruments. The outer core, sloshed, the inner core, felt the torque, and the mantle shared angular momentum. That's not poetry. It's a check on whether our decadal oscillation story holds water, and a setup for the next reveal. Deeper still, geodesy keeps the clocks honest. Very long baseline interferometry times radio signals from distant quasars at antennas continents, apart to measure Earth's rotation precisely. Satellite laser ranging and GNSS track the planet's wobble and length of day changes to fractions of a millisecond. Feed those records into the assimilation, and the core flow solutions must account for the angular momentum. Bookkeeping, we actually observe. If a proposed flow would lengthen the day and the geodesy says it's shortened, back to the drawing board. Space weather monitors close the loop on the outside. Coronagraphs watch for halo CMEs. L1 sentinels measure solar wind speed and magnetic orientation an hour upstream. Ground magnetometers map induced currents. Those feeds don't tell you about the core, but they tell you when external noise will swamp the signal. A model that pretends the magnetosphere is quiet during a storm will blame the core for a wiggle it didn't write. Human moments glue the stack. In Hermanus, an observer resets a century-old variometer and sends another clean day curve to the network. In Copenhagen, a swarm engineer rejects a day of data because a thruster firing fouled the calibration. In Paris, an assimilation run finishes overnight. A plot shows the African reverse patch nudged west by a hair with narrower error bars. A note goes to a satellite ops list. Consider extending the South Atlantic mask by 60 seconds for orbits with local time near dusk. In a seismic lab, a student aligns PKIKP pairs and drops a point on a decadal trend that matches the latest LOD turn. What's next isn't mystical, it's coverage. Ocean bottom arrays to fill the blue deserts. Swarm-class successors to keep the movie uninterrupted. a higher orbit magnetometer to model the magnetosphere away from the core signal, better clocks at ground stations and tighter calibration among satellites, and more assimilation work that treats the deep Earth like a forecast target, not a history lesson. The goal isn't prediction to a date. It's heads-up time, months to years of warning that a weak zone is breathing faster, that torsional waves are back, that the dense edge just moved. Enough time for people who fly the seams of reality to adjust quietly so the rest of us never notice the core changed key. The simulation bridge, AI, quantum, and useful illusions. We've been living in physics you can touch. Iron flows, drifting poles, auroras at the wrong latitudes. Now, step across a narrow bridge where perception and construction start to rhyme. The hinge is simple. Systems don't need truth to be convincing. They need coherence at the point of contact. That's as true for human perception as it is for the newest machines we're building. Cognitive scientist Donald Hoffman calls our senses a user interface, not a mirror, a dashboard. Icons that trade accuracy for speed, tuned by evolution to keep us alive, not to reveal code. You click a folder, you don't see electrons moving on silicon. That shortcut works because the icon is useful. Our brains run the same trick. Colors, hours, distances. Good enough representations that let us act. Watch how technology is converging on the same bargain. Modern AI models don't derive meaning from first principles. They predict the next plausible token, pixel, or move. When they draft text, paint an image, or steer a synthetic agent, the measure of success isn't truth, it's whether the output holds together for us. Useful illusion, optimized for coherence. They're not broken for lacking essence, they're built to win without it. Quantum simulators push this further. Neutral atom arrays and superconducting qubits are now recreating many-body phenomena directly in hardware. Dozens to low hundreds of controllable atoms, phases switching on command, dynamics unspooling faster than classical computers can track. No one mistakes a 256 atom lattice for a cosmos, but the principle lands. If we can construct small, law-abiding domains where particles behave with internal validity, scale is only engineering in time. We're no longer guessing whether physics can be manufactured. We're watching it run in miniature. Tie those threads to the field outside the lab. The same year Swarm mapped a weak field lobe splitting, AI systems delivered photoreal scenes, live agents with memory and goals, and dialogue that, however hollow inside, felt continuous. Quantum hardware crossed thresholds where specific chemistry, magnetism, and chaos were explored natively. Put it together, and you get a working example of Hoffman's interface logic reincarnated in code. Coherence over essence. Convince the observer, and the world stands. This is where the simulation argument slips in, not as proof, but as arithmetic. If civilizations can build convincing worlds, even small ones now, bigger ones later, the ratios tilt. Simulated observers could outnumber base layer observers by orders of magnitude. You don't have to buy the conclusion to feel the pressure. When our tools begin to generate pockets of physics that obey rules, and our cognition is already optimized to accept useful surfaces, distinguishing is from as if gets slippery. But hold the brakes. Science isn't surrendering to metaphysics. The anomalies that anchor this story, inner core oscillations, the South Atlantic Anomaly, storm coupling, stand on measurements, PKIKP, differentials, satellite magnetometers, dose meters, timing logs. Simulation talk doesn't replace that. It reframes the irony. The same alignment that makes a dented shield feel jittery is the alignment that makes AI convincing. Our threshold for real enough is lower than we admit when the interface stays smooth. There's a harder edge, too. Billionaires funding longevity, quantum labs, and world-scale AI aren't publishing escape plans for a fake universe. They're hedging against messy reality by building alternate domains, extended health, alternative habitats, synthetic training grounds, digital experiences persuasive enough to capture attention and revenue. Whether they believe in simulation is moot. Their money accelerates tools that reduce how much truth experience requires. A short human moment. A developer fine-tunes a large model for mission ops. The model doesn't understand magnetospheres. It's trained to recognize patterns in telemetry and propose actions that keep satellites alive. It learns to widen SAA masks, because that's what success looked like in the logs. No physics under the hood, just predictive coherence that saves detectors. In a quantum lab, a grad student dials a Hamiltonian and watches a synthetic spin system cross a phase boundary. The apparatus knows nothing about spins, but the readout matches theory. 2 rooms, same result. Construct the interface right, and the world appears.
This isn't an argument to resign, meaning. It's a warrant to be precise about risk. If perception runs on icons, and our machines now craft icons at planetary scale, we will increasingly live inside layers where useful illusions govern behavior. When Earth's shield gets noisy, the layers blur. A dispatcher trusts an AI agent's route suggestion because it's usually right. A grid operator trusts a forecast because the last storm followed its arc. A pilot trusts an instrument suite designed to degrade gracefully when GNSS scintillates. Interfaces everywhere, stitching friction into smoothness. What breaks the spell is falsification. Instruments that refuse story, for example, atomic clocks that don't care about vibes, magnetometers that don't care about rhetoric, seismograms that don't care about headlines. Anchor us. Keep those honest, and the rest can sway. That's the responsible bridge. Use simulation logic to build tools that adapt under noise while insisting that truth-telling sensors set the rails. So when people say reality feels glitchy, it's tempting to reach for mysticism. The cleaner read is practical. A dented shield plus a sun and a mood will expose seams. Our minds will smooth them with stories. Our machines will smooth them with predictions. The job is to keep the smoothing aligned with measurements. If there's a lesson from Hoffman, AI, and quantum rigs, it's this. Coherence is cheap. Fidelity is expensive. Survival rides on knowing what you're buying. Operators, pilots, and researchers. Unknown to most people, the Dent has office hours, and so do the people who live under it. In a dim flight dynamics room, Anna watches a green line slide into a geofence over the South Atlantic. Her patch, 90 extra seconds of detector downtime, costs 3 images per orbit. The proton counter stays flat. She exhales, logs the pass, and writes, "Mask extended, no upsets." 6 months earlier, that same bird took 2 watchdog resets right here and scrambled a star tracker catalog. The fix wasn't a breakthrough, it was a small surrender to a moving seam. While that's happening in Madrid, a telescope team argues over minutes. Their target needs 1 uninterrupted exposure, but the eastern lobe drift shaved the window thin. "Split it and keep the core," the principal investigator says, "or keep it whole and roll the dice." They split it. Tomorrow's calibration shows clean frames, a neat rectangle of zeros where the Dent passed. The missing photons feel like a loss, until someone sketches the instrument lifetime curve and points to years preserved by dull choices. 3 nights earlier, on a Johannesburg polar departure, Captain Gnomes watched the standby compass wander 3 degrees off primary. A GPS integrity flag blinked for seconds. The flight computer slid to inertial and DME like it was born to, and the crew flew the airplane. Dispatch had already slid their track 20 minutes to dodge an HF advisory and trimmed dose by a fraction. In the galley, a dose meter chirped 1 extra count. Nobody made an announcement. After landing, the log read, "Brief RAIM alert, compass split nominal." It's boring because they trained boredom into it. At a Brazilian grid control center, Marisol sees a space weather alert, Halo CME, arrival in 36 hours. She calls the night shift, trims transfers on long east-west corridors, tightens transformer thermal alarms, and flags 2 substations for closer watch. When the shock hits, neutral currents rise and plateau below her line. Backscatter Aurora's light headlines, her screen shows flat curves. She messages the crew, "Storm posture held, no saturation." A year ago, funding arrived for neutral blocking devices on that corridor. Tonight, they bought invisibility. In Sao Paulo's timing lab, Tiago watches a GPS-disciplined clock through a transient. The backup oven-controlled oscillator eases in. A second feed, fiber-delivered time from an atomic source, holds phase. Phaser displays keep painting steady angles. He circles the blip and emails the operator. GNSS scintillation event, no loss of sync, fiber plus XO carried. This is what resilience sounds like, acronyms and a shrug. Down south, a Medevac crew out of Punta Arenas loses HF for 10 minutes, crossing a lively patch. They go to SATCOM, lengthen the call tree, and march through a slower checklist. A dose advisory nudges them down 2,000 feet for a leg. The patient never hears the term ionospheric scintillation.
The pilots file a report that reads like a detour around weather. Back in Cape Town, Naledi and Ben kneel by a kiln trench. They mark the mouth with a sun compass because iron-rich rocks can lie. In the lab, tiny magnetic grains in the fired clay give low intensities for a run of centuries that match a sediment core offshore. Down the hall, Tabo runs a geodynamo with a steeper African LLSVP edge and watches a reversed flux patch swell and slide west of Hare. They pin plots to a corkboard. Someone writes close between them. Not proof, rhythm. Cameras don't roll when small satellites learn the hard way. A CubeSat with consumer-grade flash crosses the eastern lobe in a bad mode. A single event upset slips past ECC. A configuration bit flips, and the safe mode triggers mid-downlink. The team loses a day and a little swagger. They meet, move the mode, change 5 minutes earlier, raise the scrub rate, and tape a printed spectrogram with a hand-drawn mask line above the ops console. Next pass, the log is calm. In Toulouse, Rami drags a tabletop proton source next to an avionics board. He dials a flux profile pulled from SAA transit logs. Soft errors bloom until a new scrub schedule flattens them. He snaps a photo of a dead straight line and texts his mother. "It's good," he writes. She replies with a heart, not knowing she just hearted a memory scrub. None of them talk about reversals. They talk about windows and margins. They write patches at midnight, reroute flights quietly, lower loads ahead of a storm, and argue over minutes because minutes stack into years. The Dent doesn't care about metaphors. It rewards respect. And the people who live at its edge have learned to treat it like rain. Check the forecast, carry an umbrella, and get on with the day. Actionable Playbook, what matters now. Start with the machines closest to the Dent. Satellites live or die by small, boring choices, so lock those in. Treat radiation-tolerant memory as default, not deluxe. Scrub, configuration continuously, not nightly. Wrap clocks and high-voltage front ends in real shielding, even if it costs a kilogram. Fly with SAA-aware autonomy. Geofence masks that update in orbit from the latest field models. Raise star tracker proton flags before the eastern lobe, and fuse gyros through the pass. Pick orbits and local times that shave minutes off weak lane crossings. Price inclination honestly in insurance. Low Earth orbit isn't one neighborhood anymore. Give operations teams better eyes and earlier warnings. Tie coronagraph and L1 solar feeds to automatic timeline changes so mode shifts hit the bird before the shock hits the magnetosphere. Feed swarm-class model updates into onboard masks weekly, not annually, and keep a spare radio path warmed. Deep dielectric charging sometimes waits hours to bite. When it does, the reboot should land on a clean link. Aviation's rule is simple. Treat space weather like turbulence. Build integrated dose routing into flight management instead of stapled advisories. Track crew exposure in real time, smooth with rotation, and normalize small latitude shifts at solar max. Train for GNSS integrity blips with crisp fallbacks to inertial and DME. Keep HF alternatives on tap when polar bands go dark. Tie dispatch dashboards to ionospheric nowcasts, not just winds. Clean comms is part of safety fuel. Grids don't need heroics, they need posture. Put a GIC monitor on every vulnerable transformer neutral. Install series capacitors and neutral blocking on long east-west corridors where storm-time electric fields hit hardest. Add thermal headroom to new cores. Hot steel buys time. Drill the storm play. Reduce long-haul transfers on alert, watch neutrals, and pre-position crews. Build spare fleets and sharing agreements that move hardware across regions faster than procurement ever will. Navigation and timing keep the beat. Don't bet the farm on one sky. Use multi-constellation receivers, deliver time over fiber to critical nodes, and give local oscillators real holdover. In storm windows, trust atomic sources and fiber more than a scintillating ionosphere. Let satellite discipline drift back in when the sky quiets. For survey work, watch vertical delay estimates and pause centimeter ambitions when the map looks like static. Forecasting is the multiplier. Fund coronagraphs at multiple longitudes, an L1 sentinel with healthy margins, and ground magnetometer arrays where the map is empty. Put ocean bottom magnetometers in the blue deserts and keep a swarm-class successor flying, so core field updates don't skip a beat. Run data assimilation, like weather. Blend measurements with physics. publish core surface flow maps with uncertainties, and push a simple flag when the anomaly's lobe just moved. Operators will act if you give them time. Policy isn't romance. It's budgets that outlast headlines. Mandate GIC monitoring on critical corridors and minimum transformer headroom on new builds. Incentivize fiber-delivered time to substations and control rooms. Bake space weather drills into grid and aviation audits. Tie satellite spectrum allocations to resilience plans. Masks, scrubbing, shielding, not just throughput. Research needs continuity. Keep swapping seismology and magnetism across hallways. Inner core structure, torsional oscillations, heat flux at the African LLSVP's edge. Fund open, version field models so operators don't guess which map to trust. And back the unglamorous, calibration labs for magnetometers, overlap between missions, and quiet money for the century-old observatories that anchor the drift. Public mindset is the glue. Treat magnetic weather like weather full stop. Forecast it, brief it, and move on. If you fly, expect occasional detours at Solar Max. If you run a plant, expect drills. If you write software for time-critical systems, expect holdover. The story isn't doom, it's maintenance of a living map, and the payoff is invisible when it works. One last micro step. Put a single page above every console that says, masks by model, thresholds by storm, clocks by fiber, comms by plan. When the Dent drifts, nobody improvises. They execute, and the night stays boring. The core's rhythm didn't break the world. It exposed the seams we've been smoothing over. If you want the deeper thread, how weak shields, strong storms, and human playbooks braid together, watch the companion deep dive next. Subscribe, drop your theory, core physics, space weather, or simulation, and tell us where you